In the last chapter, we discussed some of the interactions between different molecules. So things like dipole-dipole interaction, London forces, all of these different intermolecular forces that come into play when different molecules are interacting with each other. In this chapter, we'll take some of those same ideas and we'll apply them to making solutions. So we'll talk about some of the processes behind making solutions, things like solubility, what affects solubility, and we'll get into some colligative properties at the end. So the first thing, let's just discuss some terms. So what is a solution? This is something we've heard a lot probably before, but what exactly is a solution? So a solution is essentially just a homogeneous mixture, meaning it's only in one phase. So it doesn't necessarily have to be in liquid phase. It could be also in the gaseous phase, and we'll discuss that in just a moment. But basically a solution is just a mixture of more than one thing that's all in the same phase. Okay, so we have a couple components in this mixture that make up a solution. So the first thing we have is the solvent. The solvent is just whatever the major component of the solution is. So for instance, if you dissolve something like sugar into water, water would be the solvent. The solute is the minor component, so it's essentially what's being dissolved. Okay, so in that my analogy, putting sugar into water, sugar would be the solute. So it's only a subtle difference in these two words, so let's try to keep these straight. So solvent and solute. Okay, so when a solvent and a solute come together, that makes a solution. And we will talk a lot about aqueous solutions, this word aqueous. This just means that it's dissolved in water. Okay, so a lot of solutions in chemistry, especially the type we'll use in general chemistry, will be aqueous solutions. So as I was saying before, it doesn't necessarily have to be in the liquid phase. Essentially, the solvent will be whatever retains the state. So we could have a mixture of two gases. Okay, so we could have a solution of gases where we mixed more than one gas, and we've made a solution from them, and they stay in the gaseous phase, so this would be a gas solution. Okay, an example of this would be air. Okay, so we walk around in a solution of nitrogen and carbon dioxide and oxygen. Okay, all these come together and they make a solution that we call air. Okay, or we could have a liquid-liquid solution, or we could have a liquid solution. Okay, in this case we have maybe liquid as our solvent, okay, gas as our solute, and notice we would call this a liquid solution because our solvent is a liquid. Okay, so the solution will always retain the phase of the solvent. So this would be like dissolving oxygen into water, for instance, or dissolving CO2 into a drink to make it carbonated. Okay, we could also have a liquid-liquid solution where both our solvent and our solute are liquid. Okay, this would be like putting alcohol into water, or maybe diluting an acid, for instance. We could have a solution that's made up of a liquid and a solid that retains the liquid state. Okay, so this would be like dissolving, for instance, salt into water. So the liquid will dissolve the water will dissolve the salt, excuse me. Okay, and so we end up with a liquid solution. We could have a gas dissolved into a solid, okay, such as hydrogen dissolved into palladium. We could have a liquid dissolved into a solid, or a solid dissolved into a solid even. So this is, this last one is like an amalgam. So I don't think they really use this anymore, but we used to use mercury amalgams for fillings. So you take a metal and you can dissolve it into mercury, and that's known as an amalgam. Okay, or you could dissolve silver into gold, for instance. These are also known as alloys. Okay, so notice that solutions will take on the state of the solvent. So if our solvent is a liquid, the solution will be a liquid. If our solvent is a gas, our solution is a gas. If our solvent is a solid, then our solution will be in the solid state. Okay, so now that we know what a solution is, let's talk about how we make a solution. Okay, so if we recall the intermolecular forces we talked about in the last chapter, so we have, of course, our LDF, our dispersion forces, our dipole-dipole, our hydrogen bonding, and our ion dipole. Okay, so all of these will come into play when we're talking about making a solution. Okay, and we'll see how that exactly works. So if we think about those IMFs interacting with each other, okay, so two molecules interacting with each other, and first we'll take a look at, we have a solvent-solvent interaction. So these little dotted lines just mean they're associated with each other. And then we have a solute-solute interaction. So in other words, before we combine them, those intermolecular forces are at play. Okay, so they're holding that material together. So what we have to do in order to make a solution is first realize that we have to have a new interaction. So now we have to have a solvent-solute interaction. Okay, so we have three types of interactions at play here. So solvent-solvent, solute-solute, and then we have to make a third one, solute-solvent. Okay, so for instance, if we want to dissolve a crystal of sodium chloride into water. Okay, so this is sort of what sodium chloride looks like up close, so something like table salt. If you were to look very, very close, you would see tiny little cubes. Okay, so what happens if we want to dissolve table salt into water? Okay, well, the first thing we have to do is we have to break this interaction, solvent-solvent, and we also have to break solute-solute. Okay, so in order to form a solution, this has to take place. If this doesn't take place, then we don't have a solution. Okay, so when we're dissolving something like a salt into water, what will happen is the water molecules start to interact with the ions within the metal. So in this case, sodium chloride within the salt, I should say. Okay, so essentially you have what we call ion dipole. So remember back to our four types here. So ion dipole, we're interacting with this one. Okay, remember this is a very, very strong interaction. Okay, so as the water molecules start to interact with the different parts of the salt, so the chloride ions and the sodium ions, they start to form this ion dipole interaction. Okay, so you can see here the more positive end of the water is pointing towards, remember, the anion, and the more negative end of the water is pointing towards the cation. Okay, and what we end up with is a solution where we have individual ions surrounded by water molecules. We call this hydration. That's not so important right now. Okay, but what's important is that in order to form the solute, we had to not only break solvent-solvent bond, we also had to break solute-solute bond. And the key here is that we have to make solute-solvent interaction. Okay, so that's the key into making a solution. Okay, so we can measure this change in energy. So we can say delta H of the solution is equal to delta H of the solute plus delta H of the solute plus delta H of the mixture. Okay, so what do we mean by that? Okay, so the first thing is what change in energy happens when we break those solute-solute interaction? What change in energy happens when we separate the solvent molecules? And lastly, what change in energy happens when we mix the two together? So when we form those new interactions. Okay, so here you can see the solute molecules separating, the solvent molecules separating, and lastly forming our new mixture. Okay, so one thing I would like to point out here is that in order for this to happen, okay, it has to be somewhat, so the interaction between the solvent and solute has to be comparable to the solute-solute interaction and the solvent-solute interaction, or solvent-solvent interaction, excuse me. Okay, in other words, it has to be strong enough, so it has to be strong enough to break the solute-solute or solvent-solvent bonds. If it's not, then we don't get a solution. Okay, let's take a look at this energetically. So we just discussed that we can calculate the energy for this. Okay, so we'll calculate our delta H. So let's take a look at this in terms of energy. So on our y-axis, we have enthalpy. Okay, in our x-axis, we have really nothing, just a label saying this is an exothermic solution process. So let's take a look at this. So the first thing we see is that we have a positive change for delta H of the solvent. Okay, we also have a positive change for delta H of the solute. Okay, so what is that telling us? What does a positive delta H mean? Remember that a positive delta H means it's an endothermic process. In other words, it takes energy to break these bonds. So to go from a clump of solvent to separated solvent, we have to put some energy in order to go from a nice cubic, maybe sodium chloride or something like that, or even a metal. Okay, so to go from a nice clump of metal or a nice just clump of solute, whatever it is, doesn't really matter, to being separated, so separating into ions or separating into molecules, whatever it is, okay, that also takes energy. So our overall total for our delta H of solute and our delta H of solvent, this would be an endothermic process. Okay, so how do we come up then with that this is an exothermic solution? So what we have to look at is our final term. So that, remember, we also have the delta H of mixing. Okay, it turns out this is largely exothermic. And it turns out that the net, so if we add all these together, and we finally have a negative term for our delta H of mixture, it turns out that the net overall delta H is actually negative. Okay, so it's less than 0. So our overall solution process, so the overall process for making the solution, is exothermic. So it's overall, even though it takes energy to break the solvent, it takes energy to break the solute, overall the delta H of mixing is greater than both of those, and it's exothermic. Okay, so our net delta H would be exothermic. And the opposite is true for an endothermic process. Oh, and I should mention that if you were to do this process, if you were to do this in the lab, you mix two things together and you touch it and it feels hot, okay, that's an exothermic process. So this is maybe what's at play there. Okay, and the opposite is true for an endothermic process. So I can have positive delta H for my solvent and solute. Okay, so in other words, endothermic process. But if my delta H for mixing can still be exothermic, but if it's not greater in value and greater in amplitude than these two terms combined, okay, then I end up with a delta H greater than 0. Okay, so I end up with an endothermic process. So this solution might feel cold to the touch. Okay, so energetically speaking, that's what we're talking about. Okay, so we can have endothermic processes and we can have exothermic processes in terms of making solutions. And one particular type of solution we can talk about is when we dissolve something like sodium chloride into water. So our example from before. Okay, we can calculate delta H for this process. And when we do this, I mentioned earlier that this was called hydration. Okay, so we can measure or calculate delta H for hydration. Okay, so the enthalpy of mixing is also called the enthalpy of hydration. And this is defined as the enthalpy related to the ion-dipole interactions resulting from the hydration of ions. And I don't want to dig too deep into this, but the hydration of ions is just exactly what it sounds like. So it's that ion-dipole interaction between water molecules and the ions of salt, for instance. Okay, and there's some factors that go into this. So first thing is the distance between the ion and the dipole. So the closer they squeeze in, the stronger the interaction. Okay, this has to do with size more than anything. The charge on the ion, so the greater the charge, the stronger the attraction. Of course, right? If I have a bigger magnet, it'll suck more things into it, right? Okay, and the polarity of the solvent. So if I have a bigger dipole, I have a stronger attraction. Okay, so they can get real close, they have a stronger attraction. If they have a greater charge, they have a stronger attraction. And if the polarity of the solvent is very high, then we also have a stronger attraction. Okay, and you can see some values listed here. Again, I'm not going to get too deep into this. But you see that all ions are not created equal in this sense. Okay, so everything from lithium to sodium, potassium, these all have different delta H of hydration. And I don't want to dig too deep into that. Okay, so let's talk about saturated solutions and solubility. Okay, so the first thing we'll talk about is crystallization. Okay, so this is kind of the opposite of making a solution, so crystallizing something out. Okay, so when a solute particles and a solution collide with the surface of the solid and attach. Okay, so if you remember, well, let's not go there. But so we said that basically water molecules pick the ions off individually. Well, if the opposite happens, so if I have some solid left in my container or my solution, and a hydrated ion comes crashing into that solid, it may stick there and start to crystallize. Okay, so if it has strong interactions with itself or with the other ions, it can actually start to crystallize out of solution. Okay, so this is one way of purifying things, actually. Okay, so here it says attracted by solvent, H2O, Ions leave the surface of the solid and dissolve as a hydrated species. So this is the dissolving process. So again, the water molecules coming in and picking off those ions. So the opposite, so any dissolved ion that collides with the solid solute surface can lose its water of hydration and rejoin the solid. So in other words, the ion sticks back to the solid and the water molecules go away. Okay? And depending on the conditions, so depending on things like concentration, temperature, all this kind of stuff will depend on whether it favors dissolving or whether it favors crystallization. Okay, so we have two opposing forces occurring. Okay, so we have dissolving. Okay, so that's the solution formation. And then we also have crystallization, so essentially the opposite of forming a solution. Okay, this is a reversible process. So many times, especially in things like organic chemistry or really any kind of synthetic chemistry, this process can be used to purify your product. So when you do a reaction, you want just what you were intending to make. You don't want all that other stuff, generally speaking. Okay, so we combine solute and solvent. Okay, and we can dissolve it, and that makes a solution. And then if it crystallizes back out, okay, that's just known as crystallization. There's also a term used in chemistry called crashing out. You may hear me say that from time to time. If you crash out, so it's basically just the term used for crystallization. Or precipitation, I guess, more accurately. Okay, but so the system is at a state of dynamic equilibrium. Okay, so notice we're using equilibrium arrows here. So it's not just in one direction. We can go both ways with this. So remember that dynamic equilibrium is just when the rate of the forward process equals the rate of the reverse process. Okay, so the entire time you have a solution going, okay, this system is always going back and forth, and depending on the conditions, will depend on which way it favors. So let's talk about some more terms. Okay, so we have a saturated solution. What is a saturated solution? So a saturated solution is a solution that is in equilibrium with its undissolved solute. Okay, so in other words, you can kind of think of this as just having the maximum amount of solute dissolved in a solvent. That's a saturated solution. Okay, how do we define solubility? So that's the amount of solute needed to form a saturated solution. Okay, and it says in a given quantity of solvent. So the solubility of something is the amount that you can dissolve into a given amount of solvent and reach that equilibrium. Okay, so if we're at that dynamic equilibrium, we're at our saturation point. Okay, so what is an unsaturated solution? It's just what it sounds like. So it's a solution containing less than the equilibrium amount of dissolved solute at a given temperature. And then lastly, so this is when we don't have enough to be at our saturation point. And then lastly, we have a supersaturated solution. So a solution containing more than an equilibrium amount of dissolved solute at a given temperature. So this would be like if you just kept pouring sugar into the tea when you make it, and to the point where you can't dissolve anymore, and you have an inch of sugar at the bottom of the tea. Okay, but if we think about this, we can actually add more than the solution can take. So we can make a supersaturated solution. Okay, so if you do what? If you pour that instead into hot tea, it would dissolve, right? Okay, so if you warm the tea up when you make it before you add the sugar, you can actually put that into the solution. Okay, whereas if it was colder, it would just settle to the bottom. Okay, so this is how we can have a solution that contains more than its equilibrium amount of a solute. Okay, so this is just an example of crystallization. Okay, so here we have basically a saturated solution, and it may be a little tough to see, but what this person is holding in these tweezers, okay, is just a small crystal. And this is a very common technique used in chemistry, where we actually cause something to crystallize by adding a seed crystal. Okay, so remember, in order for something to crystallize, it needs to collide with the surface of that solute. So if we have a saturated solution, or even a supersaturated solution maybe, okay, so maybe we heated this up and then we cooled our reaction mixture back down, and we want to crystallize out our product. Okay, so we can add a seed crystal, and as those collisions start to happen, we start to form crystals of our solute. Okay, to the point where we can crystallize out the majority of our product, and maybe we even chill it down a little bit to get some more of that product out. Okay, and as a result of that, we end up with these crystals. Basically, we end up with solid solute. Okay, so we've brought that solute back out of solution. Okay, so just a couple more solubility terms here. So if something is soluble, it refers to a solute that will dissolve in a solvent. If something is insoluble, it refers to a solute that will not dissolve in a solvent. Okay, and if something is miscible, it refers to a solution where the solute is infinitely soluble in the solvent. So this is like maybe an alcohol in water. Okay, if it's immiscible, it refers to a solution where the solute has a limit to its solubility in the solvent. Okay, often used just to say something won't mix at all. Something like oil and water, you could say, is immiscible. Its limit would be very low, in other words. Okay. So I said there's some factors that affect solubility. So let's get into those factors. Okay, so the interaction between the solvent and the solute is one factor. Okay, so remember we said that it has to have a favorable interaction. Okay, enough to break the solvent-solvent bonds and the solute-solute bonds. Okay, the temperature of the mixture. Okay, so generally speaking, if we heat a solution, the solubility of something goes up. Okay, and the outstanding pressure, or the outside pressure. So for instance, if I want to dissolve more of a gas into a liquid, or maybe just a bigger gas mixture, okay, the pressure will affect it. Okay, so in general, when other factors are comparable, the stronger the reactions between the solvent and the solutes, the greater the solubility of the solute in the solvent. Okay, so what is this saying? So it's just saying that if the solute and solute interact very strongly, so if there's a strong attraction there, generally speaking, the solubility would be greater. Okay, the solvent-solute interactions we need to consider are just our IMF. So this is our ion dipole, dipole-dipole, and dispersion and hydrogen bonding. So just like we talked about before. Okay, so all of our IMFs are in play here. Okay, so polar solvents or polar solutes dissolve in polar solvents. Nonpolar solutes dissolve in nonpolar solvents. So we use the adage like dissolves like, meaning that, again, polar goes into polar, nonpolar goes into nonpolar. Sorry, that's kind of a squiggly L there. So if we take a look at this, so we have some alcohols here. Okay, so generally speaking, an alcohol would be a polar compound, of course. Okay, so if we take a look at their solubilities in a polar solvent, water, and their solubilities in a nonpolar solvent, so this is hexane. Okay, so if we look at methanol, okay, so this is our most polar example, and we're going to work towards less polar examples. Okay, so if we notice, it's infinitely soluble in water, meaning we can dump all the methanol into water that we want, and it'll just continue dissolving. But notice it has a very limited solubility in our nonpolar solvent. Okay, and as we increase the nonpolar nature, so we're adding a carbon each time we do this, so we go from methanol to ethanol, still soluble in water, but now notice we've actually become soluble in nonpolar solvent. So how have we done this? Well, we've increased the nonpolar nature of the alcohol. Okay, so we've extended that carbon chain tail. Okay, so remember that things like carbon chains, so if we just had ethane, for instance, this would be a nonpolar molecule. Okay, but by adding that OH up front, we now made it a polar molecule. But as we add carbon, we start to enhance that nonpolar nature. Okay, so we go from ethanol, now we go into propanol. Still soluble in water, still soluble in our nonpolar solvent. We go to butanol. Now notice, we've added so many carbons, and we've extended that nonpolar nature so much, now we're starting to limit our solubility. Haven't limited our solubility in nonpolar solvent, but in our polar solvent, now our solubility is becoming limited. And as we keep going down the chain, you can see that it goes less and less soluble, or becomes less and less soluble, I should say. Okay, while still maintaining its solubility in the nonpolar solvent. Okay, so hopefully this kind of demonstrates to you that nonpolar solvents go into nonpolar, or nonpolar solutes go into nonpolar solvents, and polar solutes go into polar solvents. Okay, and if I want to make something more soluble in a nonpolar solvent, I can maybe extend the carbon chain, something like that. Okay, oh, I actually had that written here. Okay, so like dissolves like. Just a good way to remember that. Okay, so one way to increase the solubility of a solute in water is to increase the number of polar group it contains. So this is the opposite. Okay, so here we have cyclohexane. Okay, so it has no polar OH groups, and it's insoluble in water. So what happens if we start to add OHs to this? Okay, so OH groups enhance the aqueous solubility because of their ability to hydrogen bond with water. Okay, so since the OH groups can hydrogen bond with water, now that's a strong favorable interaction with the solvent. So this is an example of glucose. So it has 5 OH bonds, or 5 OH groups, and it's highly soluble in water. So it's a sugar, of course. It would be soluble in water. Okay, and it's due to that OH group interacting with the water. Okay, so this is a graph of solubility versus temperature. And we have a note here that says most substances, notice it says most, become more soluble as temperature rises, although the exact relationship is often complex and nonlinear. Okay, so what's interesting is that solubility doesn't always work exactly the way you think it would. So you would think, okay, if I increase the temperature by 10 degrees or by 20 degrees or by tenfold, then my solubility will increase by the same amount. Okay, well that's not exactly true. So solubility is one of these things that's a little bit unpredictable. So we're going to go over some rules in just a few minutes, or in a few moments. And that's sort of guidelines. So it's a way of estimating solubility. But what you'll find is that in the real world, solubility can be a little bit of a puzzle. So the only true way to know if something's soluble is to actually go into the lab and test it yourself. So you can predict something's solubility, but to know for sure, you have to actually go test it in the lab. Okay, so notice things like sodium chloride is pretty linear, potassium chloride is pretty linear, and these all increase, the solubilities increase as we increase the temperature. But notice cesium sulfate actually decreases in solubility as we increase the temperature. Okay, so it's not completely a black and white thing here. Okay, and the opposite is true for gases. Okay, so most gases become less soluble in water as the temperature increases. Okay, so here we have solubility versus temperature again. Okay, so if you want to dissolve more of a gas into a liquid, you actually want to lower the temperature. So for instance, at the Coca-Cola plant or the Dr. Pepper plant, when they want to increase the solubility of carbon dioxide, so to carbonate the beverage, they actually want to do it at low temperatures, not at high temperatures. Okay, so generally speaking, the solubility of a gas goes up as you decrease the temperature, and it goes down as you raise the temperature. So it's kind of the opposite of a solid solute. Okay, but one way we can increase the solubility of a gas is by increasing the pressure. Okay, so on the left we have a cylinder with a liquid and a gas. Okay, and they're at equilibrium. Okay, so we have gas particles or gas molecules going into the solution and out of the solution. If we were to increase the pressure by squeezing the container, or just lowering the volume, we could say. In this case, they're pushing the piston. So we can actually temporarily dissolve, or temporarily force, more gas particles in the solution. Okay, so more are going into solution than are actually leaving. Okay, but eventually, if we let this stay in these conditions, the equilibrium will be restored. And what we've effectively done is we've increased the solubility of that gas in that liquid. Or not increased, but increased the amount dissolved, we should say. Okay, so another example, if we're in the business of carbonating soda. Okay, do we want to do it at low pressure, or do we want to do it at higher pressure? Okay, so if we think about opening a can of Coke, what happens? The very first thing you hear, right? So what are you hearing? So the bottling plant, or the canning plant, I guess we should say, has increased the pressure, lowered that temperature, and they've squeezed as much carbon dioxide as they can into that Coke. Okay, so what have they done? They've lowered the volume, essentially, increased the pressure. So what are you doing when you open the can? You're infinitely increasing the volume, right? Okay, so a lot of that gas that was forced into the solution, even though you probably have it cold, okay, so all of that gas forced in that solution can now leave because you've relieved that pressure. Okay, so you've infinitely increased the volume. Okay, so a lot of that gas is going to leave the solution. Okay, and so here we can say that the solubility of a gas in water is directly proportional. It's directly proportional, so they're hand in hand, to the partial pressure of the gas. And by partial pressure, this just means essentially it's the percentage of that gas in the mixture. Okay, so the partial pressure is just the pressure of that one gas specifically. Okay, so if we're talking about, say we have a mixture of all these gases, so oxygen, carbon monoxide, nitrogen, helium. So if I wanted to say what's just the pressure of oxygen in that solution or in that mixture, okay, then I would refer to the partial pressure of oxygen. And again, our units are generally given as millimole per liter. Okay, but they can be in anything. Okay, any units of concentration. So generally speaking, as we increase the partial pressure of a gas, it's going to increase the solubility. And this is governed by Henry's law. So Henry's law tells us that the solubility of a gas in a liquid solvent increases in direct proportion to the partial pressure of the gas above the solution. So notice it says above the solution. So remember vapor pressure? So remember we said there's always some gas. Well, that in that terms we were talking about the liquid, but this is essentially the same idea. So it's the gas sitting above the solution. Okay, so if we go back to our example here, remember, how do we affect the solubility? We change the pressure here by lowering the volume. Okay, so that's what we're talking about. Okay, so we can just say that the solubility of a gas, so S subscript G, is directly proportional, or is proportional, to the pressure of that gas. And it turns out they're directly proportional. So we can write Henry's law. So we can say the solubility of a gas is equal to our Henry's law constant times the partial pressure of that gas. Okay, where Kh is our Henry's law constant. Okay, so pretty simple formula. Just three variables here. So we have solubility, a constant, and then our pressure. So how do we use this? Okay, so suppose we wanted to calculate what pressure of CO2 is required to keep the concentration of CO2 equal to 0.12 molarity in a soda at 25 degrees C. Okay, then they give us our Henry's law constant for CO2. And notice that this constant is specific for CO2. Okay, so each individual gas will have its own Henry's law constant. So they're not all the same. Okay, so how can we calculate this? Well, what we want to know is if S sub G is equal to 0.12 molar, and we know our Kh, we want to know what pressure would that gas have to be at? What would the partial pressure of the gas have to be? Okay, so we'll grab our Henry's law, and we'll rearrange it. So to rearrange this, our formula is just S is equal to K times P. So if we're trying to solve for, that's a terrible looking P, huh? Okay, so if we're looking to solve for P, just dissolve or divide both sides. So dissolve so many times. Divide both sides by K. So K will cancel here. We're left with P is equal to S over K. Okay, so now all we have to do is plug in our S, plug in our K. So 0.12 molar divided by our constant. Okay, so here molarity will cancel with molarity. And remember that if you have in the denominator 1 over something, when you flip this back up to the top, it becomes its natural form. So it just becomes that over 1. Okay, so this would just become ATM. Okay, so if we have a partial pressure of 3.5 ATM of CO2 at 25 degrees C, and remember, our temperature is a factor here, then we will have a solubility of 0.12 molar. Okay, so pretty simple, I hope. Okay, so give this one a try. It says, what is the concentration of oxygen in a freshwater stream that is in equilibrium with air at 25 degrees C and 1 atm? Okay, so they're giving us a temperature, give us a pressure, and it says the partial pressure of oxygen in air is 160 millimeters of mercury, and the Kh of O2 is 1.66 times 10 to the minus 6 molar per millimeters of mercury. Okay, and they want us to express our answer in grams of oxygen per liter of water. Okay, so pause the video, give this one a try, see how far you get. If you get stuck, turn the video back on and we'll go over it together. Okay, so let's take a look at this one. So they've asked us to calculate the concentration of oxygen in a freshwater stream that's in equilibrium with air at 1 atm. And they give us the partial pressure of oxygen in units of millimeters of mercury. And they give us the KH for oxygen at that same temperature in millimeters of mercury. And they want us to express our answer in grams of oxygen per liter of water. So first thing, let's just write down what they told us. Okay, so they told us that we have a P of, what are we dealing with here? We're dealing with oxygen, right? So we have pressure of oxygen equal to 160 millimeters of mercury. That's okay. An H. Millimeters of mercury. And we have a temperature. We don't really need it. Just make sure. So the only reason to use the temperatures is just make sure that these two temperatures line up. If not, you can't use this constant. So our K, Henry's law constant, is 1.66 times 10 to the minus 6. Sorry, that's a 6. Okay, and they want to know how many grams of oxygen per liter of water that is. So what's the concentration of oxygen? Okay, so in other words, we want to know solubility of O2, question mark. Okay, so that's our question here. So since we're dealing with the Henry's law constant, we're dealing with pressure of a gas in a solution, we know that we want our Henry's gas law constant. So we're going to say solubility of O2 is equal to KH times pressure of O2. Okay, and they told us our KH, they told us our pressure. Okay, so conveniently they gave us our KH and our pressure in the same units. Okay, if they didn't, so they're both in millimeters of mercury. If they did not do that, we would have to convert them. Okay, but they were nice to us, and they gave us the same units. Okay, so now let's plug in our numbers. Okay, so our solubility of oxygen will be equal to, so our KH, 1.66 times 10 to the minus 6, and that's in units of, forgot to write them here. Okay, but that's in molarity over millimeters of mercury. I just want to write K's for some reason instead of H's. Okay, so molarity over millimeters of mercury. Okay, so I'll just put this in parentheses, and we're going to say times, slide this over a little, just times our pressure. So what's our partial pressure of oxygen? 160 millimeters of mercury. Okay, so our units here, so we can say millimeters of mercury, cancel with millimeters of mercury. Okay, we're left with units of molarity. Okay, so our answer comes out to be solubility of oxygen will be 2.66 times 10 to the minus 4